All right. Going back and reminding you about these valence electrons. These are the electrons in the outermost shell of any element. And some are shy of few electrons. Things on the right side of the periodic table. Things like fluorine and oxygen. There's only 6 in the case of oxygen, 7 in the case of fluorine. What do we call those ones that are in the 7th column? Column 7 there? What do we call them, though? There's a name for that group. They're called halogens. If I didn't make mention of that there, I just did. Okay? So the halogens are the ones that have one electron shy. Chlorine, fluorine, bromine, iodine. The 8th column, or the one on the far right of the table, is the noble gases. Okay. Some of the shells only have 1 or 2 in them. Those are the ones on the left side, the metals. And they want to find someone who needs an electron. Because if they give up that electron, the shell below that is full. Does that make sense? Kind of what helped to hold the pencil the correct way. If sodium gets rid of this one electron, the one below it is a full shell. So they're happy. The goal is to have that outermost shell full, which in most cases require 8 electrons, the exception being the first row, hydrogen and helium, only need 2. So column 1, that group 1A has 1 free electron, 2 free electrons. Group 5 needs 3 electrons, 6 needs 2, 7 needs 1, 8 are just happy as clams. The other ones, those transitional elements in the middle, the ones we're kind of ignoring, because they get a little bit trickier. Yeah, I'm too tired, I'm too old. It's not going to really make as much difference for you. Okay. Remember back that Lewis diagram, diagrammed only the valence electrons that were available for exchange. So it made it a little bit easier because it only talked about the number of shells in the outermost, number of electrons in the outermost shell. So what they have the option of doing is really a couple different things. One, they can share electrons, electrodes too, but that's beside the point. And this is called, when there's electron sharing, it's called a covalent bond. Covalent. And they share a common electron to become full. So here you can see oxygen is 1, 2, 3, 4, 5, 6, 7, 8, because it's sharing 2 with carbon. And this oxygen molecule has 8. And the carbon molecule is 1, 2, 3, 4, 5, 6, 7. They're all happy because they all have 8 electrons in their outermost shell. So in that case, one carbon molecule, or one carbon atom, bonds with 2 oxygen atoms to form this substance called CO2, carbon dioxide. In addition, electrons can be can be borrowed. Where one element gives up an electron, the other one gains an electron. This is called an ionic or electrovalent bond, more often ionic bonds, the term typically used. So the example I use here is hydrogen chloride, where hydrogen gives up its electron to chloride. Chloride now becomes fully happy. Hydrogen now becomes fully happy. The only difference being is that the hydrogen now and the chloride both form what we're going to call ions. They're no longer charged neutrally. Hydrogen gave up an electron, has 1 more proton than it does electrons, so it becomes positive. Chloride gains an electron. Its outer shell is full, it's happy, however, there's more electrons than protons, so it's overall negatively charged. This is pretty exciting stuff. Okay. Stability. Stability, again, is the term that we give to an element or to an atom that is has their outermost shell full. Okay. So in the case of where chloride gained an extra electron, had 7 in its outermost, now has 8, that element is now considered to be stable. In the example of a situation where there's sometimes in the in-between stage where that outermost electron is not quite filled, we're going to call those as not being entirely filled, and we're going to call it a polyatomic ion, and I'll show you examples of those as we go along. So summing up, elements are neutral, same number of protons and electrons. Compounds are stable because their outside shells are filled, H2O, CO2. Polyatomic ions are neither stable. They still need some more electrons to complete the outer shell structure, and they're not neutral either because they have a charge one way or the other. An example of a polyatomic ion would be something like this, the bicarbonate ion. It's got some electron changes that have gone on there to create a negative charge, but it's not quite there yet. This rule of 8s or Octet Rule is that most molecules are attempting to get a stable configuration of 8 valence electrons. In that case, they won't be neutral. The exception to this is hydrogen and helium. They prefer to have 2 in their outer shell rather than 8, simply because they only have 1 shell. When we combine 2 elements chemically, this forms what we call a compound. It is a pure substance, and it's attained through the bonding of those valence electrons. A molecule is the smallest part of that compound, so multiple molecules can be put together to form compounds, but compounds are the end product that we end up having. When we talk about a certain compound, say carbon dioxide, it's present such that there's always going to be a ratio or proportion of 1 carbon to 2 oxygens. Okay, that's called a fixed ratio, and no matter how many carbons you have to have 2 oxygens going along with them to be able to join in that fashion. Are they all jumbled up? Is it there someplace?
No. Yeah. That one is sort of like missing that first bullet point.
Okay. Well, it's saying the same thing as the second bullet point.
We don't have you would do fixed weight ratio.
Right, and that's what that's what it's known as, because that ratio is going to determine what the ultimate weight of that compound is going to end up being. Oh boy.
That one we have.
Okay, let's talk about this one then. If you looked at water from anywhere that you found it, it would have basically the same physical properties as far as a boiling point, a density, a color, whatever. And those oxygen and hydrogen molecules are always combined such that for every 1 hydrogen you have 8 oxygen. Because hydrogen weighs 1 gram, you know what, that's not true. It's not 1/8, it's 1/16. No, that's right. No, I'm right. Do you have this one? Okay. Yeah. This is just basically why they end up why they're considered pure substances, is because anytime you find these elements joined together to form a compound, they're always joined in the same fashion and in the same ratio. Lots of compounds that exist. Some of them are very small. Here I have carbon joining with oxygen as carbon monoxide, 2 atoms together. And you can see situations like with DNA where that sequence is billions of atoms that are put together. All right, so what we're talking about when these valence electrons are lost, gained, or shared, that is what occurs during a chemical reaction. When you have two elements coming together, or two molecules for that matter, you either form a complete compound which is neutral in nature, or you find that polyatomic ion which is still waiting for another step to be completed. So long as that new product that is formed, here I have two hydrogen, one oxygen combining to form water in a covalent bonding process, that now is stable. Why is it stable? Because both hydrogen and oxygen have the requisite number of electrons in its outermost shell to be happy. The polyatomic ion, on the other hand, it's still not stable because there's still another electron that is needed to become complete. So example would be the hydroxide ion that is still looking for one additional electron. And an example of what might happen is something like sodium would come along, give up its electron, so hydroxide ion becomes stable, and then the whole compound becomes stable. Sodium hydroxide. Neutral, stable, everybody's got the requisite number of electrons in their outermost shell, everybody's happy. Okay? But the polyatomic ion waiting for that to happen is neither stable nor neutral. And we talked about covalent bonding being sharing, ionic bonding being where one is exchanged and given to another. Somebody receives one and somebody gives up one. We're going to come across a lot of covalent bonding in our world. Things like carbohydrates, things like proteins. Those are all basically chemical bonds that exist in the covalent process. There's also bonding that is done by sharing of electrons where you have nonmetals present. A classic example is oxygen, where it shares it with itself, or CO2. Now, one other concept that you need to be aware of is this thing called electronegativity. And it has to do with how easy or hard it is to pry that electron away. So think of electronegativity as, are you just willing to give that electron up, or are you being real stubborn about it? Things on the right side of the periodic table, things on the right that have 6 or 7 electrons in their outermost shell, they have a higher electronegativity than those on the left. In other words, fluorine doesn't want to give up an electron. It wants an electron. Things on the left-hand side, sodium, magnesium, here, take them, has very low electronegativity. So if we look at the periodic table going from right to left, or left to right, however you want to view it, things on the right have a higher electronegativity than things on the left. Things on the top of the chart have a greater electronegativity than things further down that have more rows down. And if you think about it, it makes sense because as you get further and further down the table, the atomic numbers get bigger and bigger, meaning the number of protons and electrons become greater and greater. So the further that outside valence electron is from the center, the less hold it has, that the center has on it. So it's easier to peel off those. So if we look at a chart and identify where fluorine is located, identify where mercury is located, you can see that fluorine is much higher up. It's a couple of rows up, meaning it's going to have a higher electronegativity than mercury. Does that make sense? To the right versus the left, to the top versus the bottom. So I would feel comfortable on a test giving you two elements and saying, atoms of this element, who has a greater electronegativity? Who's ever to the top right is going to be higher. You're asking a lot. Yeah, I will provide a periodic table. However, I will tell you it does not have the chemical name on it, because that's one of the things you have to identify as certain elements.
What do you mean? Don't have the abbreviation. Oh,
Yeah.
yeah. Okay.
I'll have this. I'll have the atomic number. I'll have the atomic mass. And that's it. Now I'm going to give you a blank periodic table, and you got to fill it in. Seriously? Did they really?
Yeah.
Wow, that's mean.
They did it, yeah, they did it like 10th grade. We also had to do the electron
I'm glad I went to.
configurations for every.
Huh?
I said at my high school we had to do the electron configurations for every.
Oh, and which spin goes where, and forget that nonsense. Aren't you glad you have me? Yeah, you say that now. All right. We talked about ionic compounds typically being a metal and a nonmetal. Sodium chloride, potassium chloride, calcium bromide. Those are all examples where a metal and a nonmetal join together to form a compound through the exchanging of electrons. We know that what ends up happening, especially when you put these into solution, they dissociate into basically two ions, where I have a positive sodium ion that I'm going to call a cation, and again, T meaning positive, a negatively charged anion because it's picked up an extra electron, and being for negative. And there is this idea that the number of electrons lost or gained is something we're going to call electrovalence. So in this case, the electrovalence would be 1, because one electron was given up, one electron was accepted in this marriage. In the case of calcium bromide, if we take a look at the periodic table, calcium's in the, it should be BR2 actually. Calcium, I believe, is in the second column. Correct me if I'm wrong there, guys. Bromine, I believe, is in the 7th column. So you end up having a electrovalence of 2, because there's 2 electrons that calcium has given up. Am I right, Becky? Wow. That'll stop real quickly. Does this concept make sense? Okay, good. We're going to come across a lot of ionic bonding, both in fluid and electrolyte balance as well as acid-base balance. And you don't need to know this quite yet, but an acid and a base, when they come together to neutralize itself, the resulting compounds are a water and a salt. Give you an example. Sodium hydroxide and hydrochloric acid end up forming sodium chloride and water. But that's getting a little bit ahead of the game. So let's take a look at salt. Salt's a metal, or sodium's a metal. Low electronegativity. Go ahead and steal my electron, you dirty rat. Right? So sodium atom plus some energy causes the release of that electron. And now sodium becomes a cation. Chloride, on the other hand, is a nonmetal on the right side of the table. Very high electronegativity. Readily steals away that electron that sodium has given up. So chloride item plus that electron makes it an anion, and there's some more energy that is there. And this energy basically is Some is given up, some is taken, and that's one of the ways the chemical reaction happens. Now, if you take a look at these two individual elements by themselves, sodium is a poisonous. You can cut it with a knife. It's got it's a metal in its truest sense. Chlorine is a gas that is poisonous. So we put these two poisonous elements together, and we have something that's edible. Yeah. Just doesn't make a whole lot of sense, but just that transitioning of the electrons allows for that. Kind of weird. Electrolytes are the term we're going to give to that ionic compounds when they're placed into a liquid. As I mentioned before, when you take sodium and you take chloride, well, they take sodium chloride, let me rephrase that, you put it into water, those two ions split themselves up. And they basically are in the ability to separate and join at will. Because there's this charge within it, they are also good conductors of electricity. So we'll use electrolyte solutions in a lot of our analyzers. That's what I just said. They'll conduct electrical current. We have all kind of electrolytes inside of our body, and when they're not in the proper balance, havoc. These are the electrolytes that I would like you to know. And I'm going to ask you to know the normal values for these four specifically. They have unique units, milliequivalents per liter in most cases. What the hell is that? We don't want to know. Do you? No. It's the unit of measurement that I want you to know. I don't want you to know where it's derived from. It'll make you cry. But when we order an electrolyte panel as blood work on a person, those are the four primary electrolytes that we're looking at. Sodium, potassium, chloride, and bicarbonate. We should have wrote that one out. When we do an arterial blood gas analysis, these are the values that we derive. And one day, long about module H, you'll get a blood gas and you'll be able to tell me, oh, Rick, that's a partially compensated respiratory acidosis and mild hypoxemia. Bitchin'. Based upon where those values are. Okay. Sounds like fun. As you know, if you've taken med term, hypo is a term that is used as a prefix for a low level, hyper for an elevation level. So again, I might give you and ask you, okay, you got your patient's potassium is 5.6. How would you classify that? It's hyperkalemia. Potassium's weird. Shouldn't it be hyperpotassemia? You know. So this would be sodium. Again, weird. Natremia. What about sodiumemia? No, it's natremia. Hyperkalemia, the K is potassium, calcium, chloride. Okay? Hypo. When you look at how the units are, it's this milliequivalents per liter. It's basically looking at a density that is present. Density meaning how much of a substance is present per area in the unit. If we have an area like the city of New York, we would consider that a very dense population because there's a lot of people living in a very small location. You go to Montana, and you could drive for years and never see another person. So we would say it's very low density. But density is mass per unit volume. And in the example of some of these electrolytes, we'll express it as milligrams per liter. So it's the mass of magnesium that is present per liter of blood. Milliequivalence, again, uses relative electrical charge, which I don't want to go there. Just know that it's the unit for that one. But when we looked back here, phosphorus, for instance, is milligrams per deciliter of blood. These electrolytes are very important for carrying out a lot of functions, especially within areas like the kidney, the brain, a lot of different places. And the electrolytes being present within the bloodstream is what allows us to be able to measure both the nerve function as well as the changing electrolyte concentration in, say, the cardiac muscle, which is how we measure an EKG. And we'll see them used a lot. As far as those ions are concerned, they can either be simple ions. We mentioned already chloride, just being by itself, negatively charged, floating around. Could also be a poly, many atoms together. So in this case, we end up having nitrogen bonding with 3 oxygen to form an ion. And this is where, oh, I like this. What time the hub comes home is what he gets. Hopefully it's not at 4 a.m. Next time we'll talk about naming conventions. And these polyatomic ions are going to kill you. But there's no easy way to do it. It's just got to be memorization. So you'll see. We're not there yet. There's like, I don't know, 16 or 17 of them. But, you know, it's just memorization. So, yes, ma'am.
I was afraid from the previous slide because we didn't have the but I got it. And then you said about memorizing. We need to memorize.
Next time we're going to see a whole bunch of polyatomic ions whose naming convention makes no sense. But that's next time. Questions? All righty. Well, you have a good week.